In this video, we'll talk about slicing when density varies. Let's consider a seaside village. A village that's along a 6-mile straight coastline. People prefer to live near the water, so the density of people varies with X, the distance from the shoreline. And let's suppose this village is 6 miles in length and expands 4 miles inland. The question is, how can we approximate the population in this 24 square mile village? What makes this problem hard? If the density of people, the population density were constant, this would be easy. But the population density is not constant. It varies with the distance from the shoreline. So what problem-solving strategy can be applied? Well, again, we can slice slice the interval, the distance from the shoreline, so that instead of varying from 0 miles to 4 miles from the shoreline, there's a slighter variation. So again, our problem-solving strategy will be to slice, to approximate, and to sum. What is the criteria for slicing? We slice so that density doesn't vary much within a slice. And then on a single slice, we can approximate by assuming that the density is constant and take density times square miles. And then we're going to sum over all of the slices. Take a moment to think about how you would slice this. Pause the video, make a decision, and then come back and join us. Notice that I've partitioned this village into 3 strips. Basically, what I've done is I've taken the X interval, I've partitioned the X interval, which went from 0 to 4, into, in this case, 3 equal pieces. Each of length delta x, which is equal to 4 divided by 3. So in terms of labeling, I would call this x sub 0, x sub 0, x sub 1, x sub 2, and x sub 3. The population is equal to the population on the first slice, plus the population on the second, plus the population on the third. And although we can't figure out any of those exactly, we can approximate them. The population on the kth slice is about equal to the population density times the square miles, the area. So we have to approximate the population density. Let's first do an over approximation. By that I mean, on each slice, I'm going to overestimate the number of people. So I would take on the first slice the population density at x naught, and then I have to multiply by the area of the slice. The slice is 6 miles long, and now it's just delta x high. That's an over-approximation for the number of people on the first slice. And on the second slice, I take rho of x sub 1, because that's the closest that any place on the second slice gets to the seaside, and then multiply by 6 delta x, the area. And for the third slice, rho of x sub 2 times 6 delta x. And that would give me an overestimate for the number of people. Let's suppose, on the other hand, that I wanted an underestimate. If I wanted an underestimate, then on that first slice, I would approximate the density as rho of x sub 1 and multiply that by the area. On the second slice, I'd approximate it by rho of x sub 2 and multiply by the area. And on the third slice, by rho of x sub 3 and multiply by the area. Now this would give us an approximation. We have an overestimate and an underestimate. But what if I want a better approximation? I could take the average of the two and that would be better. But what if I want even better than that? Well, I decided to chop into 3 equal pieces pretty arbitrarily. We could chop into more equal pieces. We could chop it into n equal pieces. In other words, we're chopping the distance from the sea, because that's what population density varies with, into n equal pieces. So I will do that below. More generally, we can partition the interval from 0 to 4 into n equal pieces, and each one of them is going to be of length delta x, where delta x is 4 over n. And then we can label x0, x1, x2, x3, etc., where x0 equals 0, x1 equals delta x, x2 is 2 delta x, etc., and xn is n delta x. We could summarize all of this a little bit more efficiently by saying that x sub k is k delta x, where k goes from 0 to, although it's the integer 0, 1, all the way up to n. Okay, so we could use this subdivision to find an underestimate or an overestimate. I'm going to stick to the underestimate. So what we're going to do in every slice is we're going to take the farthest distance from the ocean. Basically, I'm just saying in the first slice, it's rho of x sub 1 times 6 delta x, then rho of x sub 2 times 6 delta x for the second, all the way up to the nth slice, which is rho of x sub n times 6 delta x. So still it's density times area is population. That was a little tedious to write, so I'm now going to write this as a sum. I'm summing up the population on the kth slice, that's the density on the kth slice, times the area of the kth slice. And I'm going to sum that up from k equals 1 to n over all n slices. And this is a good approximation if n is large. Now let's take the limit as n grows without bound. The limit as n grows without bound of the sum k equals 1 to n of rho of x sub k times 6 delta x. What is that? Well, this should remind you of a definite integral. In the notation that we're used to, this piece is f of x sub k. So this looks like the sum, k equals 1 to an n, the limit as n grows without bound of f of x times delta x. And that we know is the integral of f of x dx from a to b. Now, the question is, what's a and b? We know that x sub 1 is very close to 0. And if we take the limit as n goes to infinity, delta x goes to 0 and x sub 1 goes to x sub 0. So we start at 0 and x sub n is 4. So back in this expression, this is going to be the integral from 0 to 4 of rho of x times 6 dx. So when I think about this, what I'm thinking is, this is just population density times area. And I'm summing that up, where x varies from 0 to 4. Now, we would have gotten the same integral if instead of looking at under approximations, we looked at over approximations. Let me show you what that would look like. We would get an overestimate by looking at rho of x naught times the area plus rho of x sub 1 times the area, etc., where the last one would be rho of x sub n minus 1 times 6 delta x. So we'd be summing from k equals 0 to n minus 1. But if you take the limit of that, you still get the same integral. You see that when k equals 0, well, x sub 0 is still 0. And the last value of x is x sub n minus 1. But as n goes to infinity, that gets arbitrarily close to 4. So, in the end, that the integral from 0 to 4 of rho of x, 6 dx, gives us the population. Okay, let me make one clarification. A lot of times people think this limit business, that's just something that mathematicians add on. Really, you're just dividing this into infinitely many pieces. And that's not quite right. You cannot take an interval from 0 to 4 and partition it into infinitely many pieces of the same length. Think about that for a second. How long would each piece be? 4 over infinity, that doesn't make sense. But 4 over n, the limit as n goes to infinity, that's 0. That doesn't make any sense. So do you see that you actually need to start by partitioning this interval into n pieces? And then when you take the limit of the entire thing, you do get something that makes sense. But it's very different from trying to chop it into infinitely many pieces straight from the start.